Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about compressed domain processing. In the last lecture, we started discussion on image filtering, and today we will continue that discussion. So, in the last lecture, I have mentioned that there are certain convolution multiplication properties which hold in the discrete cosine transform domain or type 2 block DCT domain, especially the symmetric convolution. For symmetric convolution, this property holds. So, I discussed about these symmetric convolutions in my earlier lectures, but let us try to understand that feature once again. Suppose you have a filter response, say Hn. Hn is the filter response, and you have an image, you have an input sequence Xn. So, I am discussing with respect to one-dimensional processing. Now, instead of taking the full response of the filter response, and the filter response is symmetric about its origin. When you specify the sequence about its origin, it is symmetric, and it is even symmetric in this case, you can see. So, what we can do, so the convolutions that you perform between this sequence, that can be performed for symmetric convolutions when you simply specify only half of the filter response. Here it is the positive side of the filter response, because in the negative side you can apply the symmetric extension. Here it is, as you can see, whole symmetry extension. That means in its two end, say this end and this end, you are applying both symmetric, whole symmetric extension. About this point, for example, about this point, this response would be this, and then you get this, you get this. Similarly, about this point, once again, it will be this. So, in this case, you can show that it becomes actually a periodic sequence of period is of twice of the period of symmetry. So, that you have to find out. So, given the filter length of n plus 1, its period will be twice n. That we have also discussed earlier. And similarly, we consider a sequence xn which is of length n, and if I perform the half symmetric extension of this sequence, then it will generate a twice n periodic signal. So, as you know that convolutions between two periodic signal is equivalent to circular convolutions, or equivalent, it will also give you a periodic response, and which can be expressed by circular convolution. So, for symmetric convolutions in this case, with this kind of symmetry, so for xn, you should understand that we have made half symmetric extension. This equivalently can be this operation, that means the convolution between this and this. If I write it in the form of circular convolution of, say, length twice n plus, in this case it is twice n, and this is twice n, which is equivalent to the symmetric convolution between these two. And for symmetric convolution of this kind of extensions in the transform domain, in the discrete cosine transform domain, they are reflected with this property. They are equivalent to these operations. If I take the type 1 DCT of h plus n sequence, that means half of the filtered response sequence, and then type 2 DCT of xn. So, note that the length of xn is n and hn is n plus 1. But when you multiply, then multiply this and you will get type 2 DCT of yn. I mean, in this case, as you know that since this is also periodic, it is sufficient that only first n samples, n DCT coefficients of C1 of the type 1 DCT of h plus n is multiplied respectively for n density coefficients pointwise for type 2 density. And note also this factor which comes from due to the density expressions what we have used in the case to get it into proper scaling. So this computation is very useful or relevant in compressed domain processing, particularly for filtering, as you can understand that what you are given here, a filter response, that means this type 1 density, this could be computed only once for a filter. So in a filter, I can design the filter in such a way that I design a filter of which is of symmetric in nature and whose half response would be in such a way that if I make whole symmetry extension, I will get the respective filter response. And then if I give you a sequence xn, then I will get yn. So I will pre-compute only type 1 density of h plus n. So let me write it in this way, say hik. This is the pre-computed one, and given any density block of my input in the form of type 2 density, then I will simply multiply them to get the type 2 density of this sequence. Of course, no, while multiplying I am ignoring this multiplication of factor. It is trivial, you need to do it for keeping them in the same scale. So these computations, let us see how we can do. And another thing, another trick we have to use in this case, we have to do zero padding. Just zero paddings are used for bringing the filter length of the required length, sometimes to bring the filter lengths of the required length of n plus 1, as I mentioned. So which means actually effectively I will be doing zero padding in this at this end. Only at this end I will be doing zero padding. Through symmetric extensions, this zero padding will be implied. And so that this length becomes n plus 1 if my sequence is of length n. And then only I am performing this thing. So these are certain things we have to consider when we are applying it in the particular application. So this is a summary of what I discussed, that if I given a filter response Hn, I have to get type 1 density of it. So you should note that here to get type 1 density, actually I have to consider the only half of that filter response, and the length of the filter response should be also related with xn sequence. If it is of length n, this half length itself should be n plus 1. And then you take type 2 density, and that is how you specify it. For any arbitrary n block density, so in this case, for example, 8 point density, if it is 8 point density, then this length should be 9. This should be length 9, and length 9, of course, it will be also 8 point type 1 density. That is the theory. So if I multiply them, then I will get this result. Now this operation I can equivalently represent in terms of a matrix multiplication. So in the, as you see, these are pointwise multiplications. So if the element of HIK, which means the coefficients, density coefficients, ordered density coefficients from 0th frequency to first to n minus 1th frequency, they are arranged in the diagonal manner. And this is the diagonal matrix what we get formed by HIK. And that if I multiply, so I am denoting this kind of conversion by this kind of notations, which I will be using subsequently in my discussion, by diag of HI, which means given this vector HI in the form of vector, as you see, it's a sequence of coefficients. So if I make a diagonal, and the length of that vector will determine the size of my matrix itself. It's a square matrix. It's a diagonal matrix, so it will be always a square matrix. So we can easily show that this operation is equivalent to these operations. Let me explain a little more. Suppose I expand this DCT block in the form of a column vector, and I am ignoring subscript, superscript for my convenience of representation, and let me represent this column vector from x0 to xn minus 1. So, you can see that my output would be y0 equals to h0 into x0. Similarly, y1 should be equal to h1 into x1. So, this is how the output will be computed, and then yn minus 1 should be hn minus 1 into xn minus 1. Now, that is what is computed through this diagonal matrix. Consider the first row and the column vector. So, only hi0 is multiplied with x0, and then you get respective y0. Similarly, h1 multiplied with x1, then you get respective y1, and it goes on. So, now let us consider how this computation could be extended for two-dimensional DCT block. Now, from the theory point of view, it is the same, where as you understand that there also have to consider symmetric convolution. So, if I consider a impulse response which is full impulse response which is symmetric, then only I can perform this kind of filtering. And for example, Gaussian filter. Gaussian filter is a symmetric, it has a symmetric response, and you can if I just specify this half and using whole symmetry extension, I can get the full response itself. Now, in 2 dimension, of course, we have to consider 2-dimensional Gaussian distributions, which means I have to take the symmetric extension in all the quadrants, and only one quadrant specification would be sufficient. And then I take the type 1 DCT of appropriate size of this block, and then type 2 DCT of the input block as it is there in the compressed domain, and perform the respective multiplication. But this operation would be, so that is pointwise operation, and as you can see that it is difficult to express them in the form of a matrix multiplication in general. But there are certain filter responses which can again conveniently expressed using this kind of matrix multiplications. Why actually we are using matrix multiplications, that would be clear later on, because as I mentioned earlier also, as you have seen that for block DCT domain operations, we have finally seen for various operations we are using this kind of linear transformation in terms of matrix multiplications. And because we are doing it, so subsequent matrix multiplications, all of them could be combined together because it is an associative operations, and they will give you a composite matrix. So, you can get a single transformation matrix very easily. So, instead of considering it as a stepwise series of transformations, you can perform the same computations as a single matrix multiplication operation. So, that would reduce your computational effort significantly in many cases. So, in this case also we would like to take leverage of that factor, and because of filtering operations which looks like a pointwise operations, to linearize that operations we have used the diagonal matrix for matrix multiplication. But any arbitrary 2-dimensional filter response, though it may be symmetric, but still it is in this form it is not convenient to express in this form of matrix multiplication. But one particular type of filter response, once again, as you can see that separable responses, which means I can factorize the two components, factors of filter response in 2 dimensions completely in a separable form. So, I can apply one of this component, one of this factor for a particular dimension by keeping the other things without disturbing it. First we do that thing, and as we have seen earlier also for separable transformation. So, you transform the columns, then transpose it, then transform the rows, then transpose it, and that would be your result. So here also you will be doing like this in these operations I have shown here. Say you have a n cross n two-dimensional DCT block of your input. So its columns are transformed by that diagonal matrix multiplication. So all columns are transformed. Then you transpose it, and then you transform its rows. Since you have transposed, those becomes columns in the transpose matrix. So again, by these diagonal multiplications, diagonal matrix multiplications, and finally you take the full transpose of the whole operations. So it would reduce these expressions in this kind of form, looks like a quadratic operation. So the pre-multiplication, and since transpose operation for diagonal matrix is the same, it will give you the same matrix, same diagonal matrix. So you may ignore these transpose operations for your simplifications. So simplified expressions. So you get the pre-multiplications of this diagonal matrix and the post-multiplication of the diagonal matrix with respective transformations, with respective type 2 DCT, type 1 DCT of those factors. Now here I have shown with the same form, it could be also say Hx into Gy. So in that case, we can have this one as Hi, that means type 1 of Hx, and this will be say Gi, which is type 1 of Gy. So this is also possible. So the result of these computations, let us try to observe. Let us observe the result of this computation. Here we can see that this is this image, the original image, which we call, actually it's a part of the Lena image. So this has been convolved using a Gaussian filter response, using a Gaussian impulse response, and with certain standard deviations with some parameters which is not specified here. And we have done only linear convolutions there. So we have considered the large filters, Gaussian filter, so that its effects are negligible, and then we apply over that mask is convolved everywhere. So it's a spatial domain operation. So this is the linearly convolved images. Now for the same filter response, of course, it has to be truncated by n+1 samples, as you understand now. And then if I apply type 2, type 1 DCT, and then multiply that type 1 DCT with each 8x8 block, each 8x8 block of the of the input image, that means DCT block of the input image, and then again in the output, those are the processed DCT block, and perform the inverse transform and display it here. So we can see that quality of this particular processed result is quite degraded than what the quality we get these images. So particularly you may observe that there are certain blocks which are very much visible, which was not visible if I look at this zone of this image, and if I look at this zone of this image, you can see those appearances of those blocks here, and we call them as blocking artifacts. And it happens because of two factors. One is that even the filter response is truncated, but the major factor is that your assumption here, since you are simply applying on a 8x8 small 8x8 block, the outside is considered as 0. Though in the original image, that there are neighboring informations, and those are accounted for filtering in the linear convolutions. But in this case, for each 8x8 block, outside is considered as 0, and then that is the equivalent convolutions what is happening. So those discontinuities, so sudden discontinuities, that is causing this kind of blocking artifact effects. So this is a problem when you apply filtering directly in the DCT domain with 8x8 blocks. So what is the way out? There could be some remedies of that. So let us consider that also. So one of the policy could be that instead of applying to a small block, why don't you apply to large block and use that result? But since you have the constraint that your input is always in the form of 8x8 block, also your output should be also in the form of 8x8 block. Now, that is the requirement of compressed domain processing in the block DCT domain. So, what you can do, that's in the intermediate step, you can perform block composition. So, we discussed about block compositions earlier also for resizing. So, here also you see that you can perform block composition. So, you get a larger DCT block. Suppose here I have shown say 16 DCT blocks. In this side there are 4 cross 4 DCT blocks. There are 16 DCT blocks. So, if I merge them, then the dimension of this DCT block would be 16 into 8, and this side is 16 into 8 and this side is 16 into 8, which is 128. So, it is 128 into 128 DCT block. It is quite large. So, the effect blocking artifacts would be only visible at this in these cases, but most of the areas will remain free of blocking artifacts. Still there will be blocking artifacts, but we are reducing it. So, you get this result after you perform the convolution, and since it is a larger block, your filters could be also, filter length could be also large. So, the truncation of filter length, that effect is also getting reduced. And then when you get this result, finally again you have to apply block decomposition, and then you get once again this kind of filtered images. So, this can give you a better quality image. Now, these operations, and there we would see that how these diagonal matrices for the convolution multiplication property, use of diagonal matrices are becoming useful, because you know that if I use a DCT block, say I am again with respect to one dimensional DCT block I am considering, that means a column vector, then I can transform it. So, a adjacent DCT block, say x1, x2, x3, say there are 3 DCT blocks. So, I can compose it into a larger DCT block, which is of size say 3n, and then I perform the respective convolution multiplication operations, that means multiplication operations with respect to my type 1 DCT. And now my type 1 DCT filter length would be also large, and they should be 0 to 3n minus 1 length. That is the length we are considering here. So, in this case you have to take 3n minus 1, because if it is n minus 1, then it becomes 2n. So, instead of n plus 1, it should be n minus 1 per DCT block. That is why it is 3n minus 1. So, this is the length, and I made this kind of diagonal block. After the block decomposition, I apply the inverse operation. Now, incidentally, this merging or decomposition block is also orthonormal. So, if I take the transpose operation, that is sufficient. So, that is why I have written transpose instead of inverse, but it looks very simple computationally, just transpose. So, then that is what this total thing will give me the finally decomposed filter blocks. That means, in my filtered block also I have y1, y2, y3. So, what I can do, the whole thing, because these are all linear transformations, I will simply multiply them into make a composite matrix of this of size 3n cross 3n. So, now you can see that this becomes my new transformation matrix for filtering, where the filter response is also a parameter. So, depending upon a filter response, I can always derive this transformation matrix, and if I multiply with the block DCTs of a column vector, then I will get the filtered column vectors. So, I have just mentioned that we do block composition, then multiplication, then block decomposition. So, this operation again I can extend it in 2 dimension again for the separable consideration, as you must have guessed that what I will do. Now, I have a single, so I can write it in this way, that I have the block x, x1, x2, x3, and I have the filter transformation matrix U 3n cross 3n. So, these are all block of n. So, total it is 3n cross 1. So, there I will get the filter response y1, y2, y3. right? So this is what we are getting. So this is composition, multiplication, decomposition. So exactly this is what I have also shown here. So in 2D, once again, since it is a transformation of columns and then transformation of rows, and then the whole thing can be simplified in this expression. So I am not again repeating the same arguments what we did earlier. Now you should be able to understand that why you do require a pre-multiplication and post-multiplication, and it is sufficient to use U and U transpose operations there, right? So this is what and so given here you can see that I have taken this as 3 cross 3. So 3 cross 3 adjacent blocks, in this size also 3, in this size also 3. So with 3 cross 3 adjacent n cross n density blocks, I am also producing filtered 3 cross 3 adjacent n cross n density blocks, and in this way I will be getting my results. Now still, as I mentioned, that you still get the artifacts in the boundary. So let me explain. Say you have, as I mentioned, 3 cross 3 input block. So this is 3 cross 3 input block, and which is also processed into a 3 cross 3 adjacent blocks, I should say, that on each of size of n cross n. So which means total size is 3n cross 3n, as you can see. So all 9 blocks are transformed into a 9 blocks for the processing. But central block it mostly remains unaffected. It is as good as it has been convolved using linear convolution. But what happens, these border blocks, they are disturbed. They are disturbed because of the assumption that outside you have zeros, as it was for small blocks. Similarly, here also outside you have zeros. So they have the effect. So there is a strategy what we can do with more computation. Say I will apply these operations for larger block, but while saving, I will save only the center block. So I will be using overlapping, I will be computing it in an overlapping way. So this is overlapping and save filtering algorithm. So this is what is described here. So it's the same operation. You only while saving, you accept only, since I have shown with respect to 4 cross 4, so I am saving 4 central blocks here. So this would improve the quality at the cost of more computations, because you are doing many redundant computations. So this is a strategy in this case with respect to 3 cross 3 adjacent blocks. You only save this part and don't use this one, and you go on doing it, but you do a lot of redundant computations, save only the central block. So this is the effect. You can see that for when you are applying the algorithm for larger blocks, though your artifacts are substantially reduced, but you see that you get the larger blocking artifacts. You may also you may also visualize that part. See here near the eyes also you can see there are artifacts of larger blocks because of merging of the blocks. But when I am taking this kind of thing, so it is almost these are almost removed. So this is almost like a linear convolution. Okay, another strategy to reduce the computations that I told about, a lot of redundant computations. What you do, you just perform. You don't do redundant computations, but for every block, say for this central block, you can observe that what is its contribution to these blocks. So it's like impulse computation. So in the DCT block, you perform that computations. So you simply once you compute them, you don't compute. So while processing this, you also you also process. So, which means that I will be assuming my outside is 0 and this is my central blocks in this with respect to this. While computing the larger filter, I will get also. So, I will be considering these are 0 blocks. So, I will be just merging them. I will be by setting them 0. In the output block, you will get also this sum response here. Now, those are the effect of X22. So, in the overlapping way, you perform for every block, you do these things and you simply add them to get the result. So, almost equivalent computations, but here it can be shown that there is significantly reduction of computations. So, this is we called actually the accumulation of neighboring blocks effect. So, contributions of the neighboring blocks, all other blocks in the input set to zeros. So, add accumulated contribution at every block. So, there, just to summarize, you can independently filter every block by padding zeros around it as I mentioned. Then you compose it to a larger block and then decompose the final result. And those decomposed blocks are contributions. And then go on doing for every block, and for respective block positions, all those contributions are added. And that is how you get the full thing. So, diagrammatically it is also showing that this is the central block and these are all zeros. These colors are showing zeros. This is the merged block, and finally whatever you get, this is the filtered response. Now, these are the contributions. So, finally you accumulate all these contributions to get the filter response. So, this is one of the applications of filtering. Actually, the result is equivalent what we have shown for overlap earlier, the overlap and save strategy, and this is the overlap and add strategy. Here one application I will show, that is for removing of blocking artifacts. For a high compression in the JPEG, these blocking artifacts are visible for decompressed image. So, you have those blocking artifacts of the decompressed image. So, what we can do in that compressed domain itself, if I perform filtering, now this is the effect that you will get using the Gaussian filtering. You can get this kind of effect, and you can see that largely these blocking artifacts are getting removed. So, directly these filtering operations you can do in the compressed domain. You can use this. Finally, these compressed images you can use. Another example is for image sharpening. So, for image sharpening, what you do, you basically add certain portion of the high frequency component. So, here that high frequency component is obtained by subtracting from the original image, again in the density block, the density blocks of the filtered image. So, those are the high frequency components of those density blocks. So, with certain factor k, and you apply for each block x. So, it is a blockwise operation. This is the operation you are doing. So, you can see that how these images, they look sharper. This is that Lena image. This is another image which is called papers. So, it is sharper. Actually, I have not shown original image. So, it may not be very clear here to you. But this is a standard image. You can find it in the literature, its original version. Even this you can apply for color sharpening. I discussed color image processing. As you know that for color images there are components, and you can have various components. So, here I have considered only luminance component. I am not going to disturb chrominance component. So, I will sharpen the luminance component and then use the chrominance component. So, if I just filter the luminance component and retain all the chrominance component and represent in the form of color, now this is a filtered image it looks like. Apply the sharpening operations of those density blocks, and this is one of the examples that how the sharpened image will look like. So, we have discussed about filtering operations. So, let me now discuss another image processing operations in the compressed domain, and this is called color enhancement operation. So we have also discussed color enhancement operation earlier, but let us see in the compressed domain how you can do it. So in the one of the standard spatial domain technique, which again you can apply for compressed domain also. Yeah, so one of the no, feature of compressed domain is that I mentioned earlier also that the DC coefficients, that means zero frequencies in the both no, direction, 0 element of a DCT block, that if I arrange those DC coefficients for each block in the same spatial order, you get a downsampled image by the factor of block size in each direction. So, but those are representative of the low resolution image. Now, if I just simply manipulate the DC coefficients, operate with the DC coefficients, there is an effect, global effect on the images itself. So, there is some of these spatial domain algorithms, they are adapted into the compressed domain just by manipulating DC coefficients. So, one of these algorithm is called alpha routing algorithm. So, what it does actually, you can see here, the values are taken, alpha roots of the values. This is the operations. Any particular value is taken in this way. So these blocks you perform this alpha minus 1 by this. It is actually taken for AC coefficients also. For all the coefficients are modified in this fashion, and that would be giving. So this y max is a parameter maximum luminance. So this is the original image, and this is the alpha routing. So in this case, we are though in the spatial domain we can do pixelized operations also in the same way, as you can see. But here it's not only DC coefficients what I was mentioning here. We'll see later on actually this kind of contrast stretching with DC coefficients are used for other kind of enhancement. For alpha routing technique, it considers all the coefficients of the DCT block and they are modified, and those DCT blocks are processed in this way, and finally the image, if I know, they have certain kind of contrast enhancement. So there is another kind of technique which is called multi-contrast enhancement, and in this case we only modify the AC coefficients. So you consider the spectral energy for kth band. So what happens that when you have a AC coefficients, or when you have a n cross n DCT block, or let me discuss with respect to 8 cross 8 block. So anyway, so this is the partitioning. So as I mentioned, this is the DC coefficient position. This is a 0 element. So this is DC coefficients. Now rest of them are AC coefficients, and there is a particular order by which these coefficients are scanned because of their frequency, order of frequency will be also increasing. So it's a zigzag order. In fact, you can see these are all off diagonal elements. So when we consider spectral energy of kth band, now each off diagonal is the corresponding band. So I will write this expression in this form: I plus j equals k, which will give me all these coefficients in this diagonal. And if I just simply add those magnitudes, I call it spectral energy. Simply magnitudes. I am not taking the square of it. That is the definition. Now, when we are measuring a contrast, so contrast of this this band is expressed in this way. So what is the energy in this band, and what is the total energy till this band? What is the total energy till this band? So fraction of energy. So this is the contrast. So here the intuition is that we can scale the coefficients in such a way that for each band there would be some kind of enhancement of this contrast measure with a weight, and there is a policy by which these coefficients could be modified, and you can perform these operations. So this algorithm, so this technique actually deals with this kind of computations by which these coefficients are modified. So, so this is the this is a factor for every kth band. You perform that, multiply the coefficients, and you can get it. Now, this operation is coupled with the DC coefficient manipulation, which means we use a contrast enhancement stretching, which means that pixel mapping function I discussed earlier, which has to be a monotonic function, and you modify the DC coefficients. Also, you modify the respective AC coefficients by using the spectral energy. So, here the expression of spectral energy, instead of using absolute magnitude, you just use square. So, this is another technique where we algorithm it does in this way. One other technique that we also will be considering here, we will be considering another intuitive definition of contrast, and in this technique what we will try to do, that we will be increasing the dynamic range of the display of the colors, or dynamic range of the particularly the luminance value and also respective colors, but the contrast, natural contrast should remain the same. So, this is the idea here, because if there is a change in the balance of those natural contrast, then the visual perception the effect of visual perception may not be very pleasing, and that effect may not be pleasing, since it is not natural. So, with this intuition, so first let us consider what is meant by, there are various ways contrast of an image is defined. One of the principle by which this contrast is also measured, or that is the Weber's law of our perception. See, our perception of any kind of effect of any kind of stimulation, it broadly it is proportional to these changes would be proportional to the respective level of which this change is occurring. If the level is very high, then you require large change to get a perceptible change of this particular factor, say brightness value. So, in the background intensity is very dark, even a small noise or small change will be perceptible. But if it is very bright like this, very white, the small noise is not perceptible, because this kind of phenomena is explained in terms of Weber's law, captured in Weber's law. You see that this proportionality, so the change as if this perception is proportional to this factor. So, you require large delta L. So, this remains kind of perceptual level. See, for the same perceptual level, you require large change for the level of measure what you have. So, in this case, it is the luminance we are considering. So, difference of luminance would be large. So, if I consider say two regions, and one is of luminance L1 and L2, this transition will be perceptible. That means, if there is a difference, that is delta L. Now, this delta L is proportional to actually either L1 and L2, or average of L1 and L2, whatever you can say. So, that is a idea. So, this can be also considered from the statistical point of view, that this delta L is a measure of standard deviation of the neighborhood variations of the corresponding variables of brightness value, and this level is captured by the, as I said, average. So, mean of that. So, this ratio. So, what we do, that if I get a 8x8 DCT block, as you can see that if I multiply these coefficients, so I will get a scaled version of that particular block if I multiply this coefficient. Okay. So, I will get that scaled version. So, the coefficient should be the same, but the question is that what is the contrast, when you are using contrast enhancements blockwise, then these factors will vary depending upon the corresponding the DC value, some mapping function. So, what we do, we first determine the scale factor from the mapping function of the DC coefficients, use the same scale factor for AC coefficients. And this is what is used for the enhancement, contrast enhancement of in the block density domain. We call this algorithm as contrast enhancement by scaling. So this is what is explained here, that we perform the scaling of DC coefficients and AC coefficients. We can do it differently, but then your contrast would be also varied in this way, but we would like to preserve them and we would like to make this scale the same. Now, when we are applying for the chroma part, there also we apply similar kind of scaling, because as you know, the color vector, if you have RGB, now if I multiply with K, still they remain the same. Your luminance will be changing, but still they remain the same color vector. The problem of earlier case is that I was only considering luminance by keeping the chroma part, say CBCR part, same without processing. Then because the luminance is changing, but since it is not changing, effectively the RGB vectors, this color vector also, there would be deviations. So it will not be the same color vector. So in this case, what we do, we also preserve the color. We also not only preserve, we are interested only on dynamic range variation, increasing the dynamic range of variations over this whole image, but keeping the colors same and also the contrast same of each block. So that's why the respective DC of the color part and AC of the color part, they are also multiplied by the same scale factor. While doing for the DC of color block, because of the representation of CBCR transformation, it's not a linear transformation, it's affine transformations, you have to perform this kind of mathematical operations. So this is the color enhancement by scaling coefficients of those blocks. So first you find the scale factor by mapping the DC coefficients with a monotonically increasing function. And you should see that this should not cross the limit of maximum level, displayable level of the display device. Then it would get saturated. It becomes nonlinear. So you should also restrict the scale within certain limit. So that is also one thing you need to observe. And so there is certain range of scale factor that is that you should use, and this is the maximum intensity of there. So apply scaling to all other coefficients in all the components, as we have mentioned in that particular expression. So for blocks having greater details, judged by a standard deviation, apply block decomposition. Here also you can see that blocking artifacts, because you are applying for 8x8 block, you will be observing blocking artifacts. So what you can do, instead of applying for 8x8 block, because this now you would like to make smaller blocks, because that would give you smoother variation. Say suppose at the lowest level, if all these meant for only one pixel, where there is no AC coefficients, then it become as good as spatial domain operations. So in this case, what we do that if the details of a block, that means its standard deviation is quite high, we decompose into 4x4 blocks and apply there, and then you merge them into an 8x8 block. It requires a bit more computations, but since you are doing it adaptively, so you are also saving many computations, but your effect is quite good. And this is a function we have used. There are various functions. These are the two functions. We call it twising function. You can see this is a form, and this is another function. And this is the scaling, as I mentioned, by which the scaling is done. And this is a kind of computational flow that you start with 8x8 block. You perform block decomposition if it is required. Otherwise, you can directly do it. Then apply CS on smaller block and block composition enhanced blocks. Only for blocks with more details, that you should notice. That is the algorithm. So you can see the effect. So this is the algorithm just for contrast enhancement of AC coefficients. This is both DC and AC, and this is contrast enhancement by scaling. There are some more results, like this is the original image, and then this is the image for alpha routing, and these are certain results for contrast enhancement by C, contrast enhancement of DC and AC coefficients. This is with twisting function using contrast enhancement by scaling, and this is another spatial domain operation, multi-scale Retinex processing, which I am not discussing here, but you can see that spatial domain operation, it requires a lot of computations, but you can see also the quality of enhanced image. So this is the original, and this is the enhanced of a spatial domain operation. And in the compressed domain, you get this operation, which is not as good as the spatial domain, but note also that the computation is much less in this case. Another interesting thing of this computation, particularly contrast enhancement by scaling, is that I can perform enhancement in iterative way. That means, suppose this is the original image. This is my original image. First, I perform contrast enhancement of scaling. Whatever operations I mentioned, you perform it, and say this is your resulting image. Now you take this resulting image as your input image. So next iteration, it will look like it. Again, from this image, you will get this image. From this image, you will get this image. So you get different kinds of effects, like postcard effects that you can see on the images. Of course, the colors are getting faded away, and also the image looks sketchy. So these are certain, I should say, manipulations that is possible over this kind of operations. The third aspect, which we will be discussing here, is called color constancy. So color constancy I also discussed during my discussion on color image processing. So in the compressed domain, it is also the same steps. You perform computation of color of the illuminant, and then you perform the color corrections on those respective pixel values. Here, as I mentioned, that you play with only DC coefficients, don't touch AC coefficients, and from there you can perform the color corrections operations. So for color of illuminant, average of colors can give you one kind of estimate of those illuminant, which is that gray world assumption, or maximum of each channel, which is the white world assumptions, and only use the DC coefficients for that. So and for the color corrections, you use diagonal color corrections. Now this can be, since these corrections are defined in the case of RGB space, you can perform the equivalent operation also in the YCBCR space. You can perform that equivalent operation, or there is another operations you can, instead of considering this kind of diagonal color correction, you can just perform chromatic shift. That means give a shift to CBCR by considering the difference between the target color and the source colors respective components. So you see that these are the shifts you are giving. So the difference between target color and source color, computations you are doing it. So these are the examples. Say this is original say image. I have shown this image earlier also. It's a kind of a manufacturing unit, and it's a bit artificially illuminated because of maybe there are certain constraints. So if I perform diagonal correction, it looks like this. If I perform chromatic shift, it looks like this. Now these are all performed in the compressed domain. Now if I perform color constancy coupled with enhancement, then you can get some interesting results. So if I consider simple enhancement of this image without any color correction, you can see that this is the effect. You can see this region where there is a red, some red box is there. This red box is slightly enhanced in this image. Similarly, the colors of others also looks little brighter. but not much of effect, not much of difference you may observe. But suppose I perform color enhancement and then I perform color correction and then I perform enhancement, the effect could be dramatic. So this is the result that you get after performing color corrections. There is of course certain color bleeding effect is there. This bluish is because of the color balance gets disturbed. That's why you have this effect. But largely you can perceive different kinds of colors. This particularly you see that there is an yellow color which was not very prominent earlier. It becomes more prominent here, these operations. So with this, let me summarize the whatever topics we have discussed under this compressed domain processing. First, we have seen that processing in this domain exploits various properties of DCTs. We have only considered block DCT compressed domain. You should note that there are other kind of compressed domain is there, like if the alternative description is in the wavelet transform domain, the coefficients of wavelets would be the representation there. We have not discussed that. We just restricted ourselves to block DCT representations. And there are certain properties of block DCTs that we used here. One is subband relationship, then block composition and decomposition operations, and convolution multiplication properties. Also scaling of coefficients for increasing dynamic range, that property you have used. Use of DC coefficients for spatial domain operations. That is also we have seen, those are the things we have used in the compressed domain. So with this, let me stop here, and we will start a new topic in the next lecture. Thank you very much for your patience and listening.